Hello everybody, this is Data 698 final thesis presentation done by Dilip Ganesan along with teammates Ali Herb and Raghunath Ramanathan. Our thesis for Data 698 is Prediction of Hospital Readmission in Diabetes Patients. First, we would like to walk through the agenda of this presentation and we will get into the details and nitty-gritty in the following slides. First, we would like to explain the research problem, the problem statement that we are trying to solve. Next, we will go about the literature review. We will talk in detail about the parameters that uh, we did the research on. Once the parameters were researched from various articles, the next step was gathering the data based on those parameters. Once the data is gathered, the next step was to define a methodology of how to go about the data exploration, data munching, preparation, pre-processing of the data sets, followed by the regression, some ensemble modeling, and finally giving a conclusion on the research statement. Moving towards the research statement or the problem statement. So we know that we need to predict patients who are diagnosed with diabetes are getting readmitted to hospital within 30 days. There is a CMS mandate, Center of Medicaid and Medicare and Medicaid Services, which has given a mandate saying like if a particular patient with certain diseases are getting readmitted within 30 days, then hospitals who are letting the patients discharged are going to get penalty. And this was enabled as part of the Affordable Care Act, and this is right now in existence. And as part of this program, not only the quality of care went up, uh, the hospitals, uh, the taxpayers were able to save a lot of money. So with that thought in mind, we dwelled further. A lot of research has happened on this particular uh, hospital readmission. What we did was we looked at all the current research that was done on that. One thing that stood out was there was no research done on the diagnosis related group. What diagnosis related group does is this is the main way in which the hospitals are getting paid. So the payment aspect of it was never considered in the readmission. More from a clinical perspective, research were done, but from a payment perspective, the researchers were not done. So we were very curious why this particular parameter was never used in the future in the previous research. So we thought, okay, this is the ideal candidate, and we wanted to see whether the DRG or the payment parameter in which the current reimbursement is happening, whether it's a positive predictor or a negative predictor or a neutral predictor in hospital readmissions. The next thing that we wanted to see is we have lots of variables in our data set. We wanted to rank and see what are the top 5 or top 6 variables which affects the hospital readmission rates. So with that problem statement set, the next thing that we dived into was the literature review. From a literature review aspect, we wanted to see how the patient parameters look like, how the medications and what medications and the kind of diagnosis that look like, and of course we wanted to look into the DRG, the payment methodology that is our topic of interest. So from a patient demographic perspective, we did a lot of research on age, uh, kids, how how kids, how diabetes in kids affects readmission rates, how diabetes in older patients affects readmission rate across races, like how it affects in African American population, Caucasians, Asians, even in Asians, how it affects Indian Asians when compared to other Asians. So lot of we went through a lot of literatures to make sure that we get a detailed understanding of all this different race related parameters, and we made a final decision saying like, yeah, race is one of the important parameters from those reviews, and we added it into the model. And next important parameter is like sex, whether females are getting readmitted more compared to that of males. So things of those angles were also researched. And once we narrowed out on the literature review part of it, the next important thing that we wanted to do was gathering of data. From a data perspective, as I said before, from previous researchers, we had the data from UCI master repository. So the data that we currently had was, or the data with which the previous researchers were happening on, they were like more often clinical claims data. So from the data, what we wanted to do was, unfortunately, that data didn't had DRG as one of the parameter. So that was a bigger problem for us. So we have the data, but we don't have DRG. So the next question was how to get the DRG. So for that, we had other parameters through which we could derive the DRG. Some of the parameters were diagnosis code, sex, age. Having those parameters available for us in the data set, the next thing that we did was finding ways to extract DRG. So for that, we found out a website called findacode.com. What this website does is, like, once you give the parameter, like the diagnosis codes, the age, and the sex, it's going to give me, for that particular setting, it's going to give me the DRG. So this was one of the findings that we figured in this research thesis. Now the next step that we wanted to do is we wanted to see our data consist, or the clinical data that we had consist of 100,000 records. So manually extracting it is like an humongous task. It's like a no-brain. It's like a very difficult task to extract the DRG related information manually for 100,000 records. So we don't want to go down the rabbit hole. So what we decided was we will try to automate this extraction. So we came up with this concept called a Selenium automation, wherein like from the data set we will import the data. We will try to hit the website findacode.com 100,000 times with 100,000 different data set, and we used beautiful soup to go and pick the DRG data exactly from the try to scrap the DRG data using beautiful soup from the Findacode website. So this was one of the interesting exercise that we did, wherein for 100,000 records we were able to extract DRG within minutes. So that was it was a challenging exercise to say the least, but it was very interesting to have the DRG data extracted. Now having the data extracted, the next step in the process was to cleanly define the methodology, like what methodology that we are going to adopt. We have the data. The next step was to explore the data, look at the data from different perspectives. We had like 56 variables in the data set. Okay, from this 56 variables, we wanted to see like what variable actually are going to give us a better prediction in terms of accuracy, and we also wanted to know whether DRG is a significant parameter. So these two are from our problem statement, these two are the questions that we are trying to attack. So we started with data exploration. Once we did the data exploration, the next was data preparation and pre-processing. We had a lot of places where like the data wasn't sufficient, so we thought like non-availability of data, and we had to remove certain variables, and there were like a lot of class imbalance in certain variables. We need to make sure that those are not getting moved into the model or getting picked up into the model. So we wanted to leave out those variables. We will be going in detail about like what kind of data explorations and preparation that we did in future slide. So once we have the data cleaned up, once it is ready for processing, the next step was to start the logistic regression. Since it's a classification problem, it's a typical classification problem, wherein we wanted to predict whether this particular patient is going to get readmitted or not. So that's our uh, that's a classification problem that we wanted to solve. So with that in mind, we started with logistic regression, and then we moved towards other classification ensemble methods and neural networks. So this was the high level methodology that we laid out for attacking the problem. Okay, next, the data exploration and preparation. So for this, let me try to walk down the slide so that we could give some detailed explanations about what kind of data exploration that we did. So as I said, there were like 56 feature set, and there were like 100,000 records. So few like there were like few variables where we didn't had data, good quality data. For example, the payer code is one wherein like 50% of the data was missing. Similarly, medical specialty, we thought like these particular variables are not going to add much to our model, so we thought, okay, let's drop it. One of the important variable that we didn't had much data was weight. The weight of the patient is directly related to diabetes, but unfortunately we didn't had weight related information for almost 90% of the data set. So we thought, okay, let's drop it. So that went out. And like that, we looked into each and every data set, and we wanted to categorize like whether it's going to add value to our modeling, or it's going to be of just uh, a variable for the sake of being there. So we don't wanted to have anything of that sort. So we thought like, yeah, we will just remove it. From a data preparation perspective, we looked it from two angles, one from clinical angle as well as from the statistical angle. From a clinical angle, what I meant by clinical angle is there are like for example, if I look at the diagnosis and the diagnosis related group, what we saw was like there were like so much of unique records of diagnosis and diagnosis related group. Like we had something like around 850 unique diagnosis codes and 500 unique DRGs. So instead of running a model with so much varied values, what we thought was we wanted to narrow this particular diagnosis and diagnosis related group into a category which to a higher level of grouping. So with that thought in mind, we came up with a disease classification category for diagnosis. So what disease classification category does is it tries to bucket these 850 unique diagnosis codes into say uh, 19 disease categories. Similarly, for DRG, there is a different set of categories wherein like uh, classification categories wherein like we grouped the DRGs into those 25 odd categories. So what we have done is from a clinical perspective, this is more like how claims are getting built. From 850 unique diagnosis code, now we have just something like 19 diagnosis codes. Similarly, from 500 DRGs, we have 25 related DRGs. So we narrowed down the data set to just a few unique data values. That's from a clinical perspective. The next thing was from a statistical perspective. There were like a lot of medication data, medication related information, which was like having lots of class imbalance, wherein the number of positives are considered less compared to the number of negatives. So we thought those are not going to add much to much to our modeling, and we made a decision to drop those values. Once those decisions were made, we wanted to plot and see uh, how the variables are looking like. So from 56, we narrowed down to 30 variables, including the DRG. So with these 30 variables, we wanted to plot and see how they look like. So are there any skewness in the frequency of the data set? Yeah, there were definitely few variables which are skewed. For example, even DRG was skewed, age was skewed. So in order to avoid this skewness, we wanted to do a log transformation, which we did when we started with the modeling. So uh, once the plotting was done, the next step we wanted to see was to check the correlation between variables as well as the predictor variable. So next we went through the correlation just to see is there any positive or negative correlation. There were like few variables which were positively correlated, but we thought like let's not take any action now. We will look into the variance inflation factor and then decide for multicollinearity when we are trying to do the when we are doing the logistic regression. So conscious decision was made to punt for a font at the time of data preparation, and to make a conscious decision when we do the logistic regression. So once from an data exploration and pre-preparation perspective, these were few of the steps that we took. And then once this was done, then we wanted to move towards getting the training and the test data set. Okay, the next step in our process was getting the training and the test data for logistic regression. So for this, what we observed was the class. Again, there was a lot of class bias in the data set, wherein the number of readmits was less compared to the number of non-readmits. So we wanted to make sure we get the right proportion of data for our training data and the rest for the test data. So we made sure, or we get the right data, meaning like equal proportion of zeros and one samples for our test data set. Once the test data set was done, the next step was to move towards starting the regression. So before going into the results of our regression analysis, let me explain the regression, uh, different rounds of regression that we did. First regression that we started was what, with the base model, wherein it had all 30 parameters, and we ran the logit model to see like what kind of accuracy, AUC, specificity, sensitivity, and the model gave. So when we ran the model for the first time, the accuracy of the model was around 67%. If I am right, okay. Yes, the accuracy of the base model was around 67%. So this model included the DRG information in it, and the AUROC curve. It's the curve wasn't so steep, but at the same time it wasn't so bad. So we had an ASU value of 62% here. One thing that stood out was the sensitivity of the model. The sensitivity, or the percentage true positive rate, in which the number of ones which are getting correctly predicted was very high. It was around 90%. So sensitivity was really high for our model. So to start with, and as I discussed in the previous data preparation step, as part of, to make sure that there is no multicollinearity, we even ran the variance in inflation factor, and we didn't see any value which is greater than 4. So all the maximum we could see is just 2.6. So there wasn't much of a multicollinearity problem. So this was our first base model, wherein we got an accuracy of 67%. So now the next thing that we did from the base model is to look for parameters which are not uh, statistically significant, or p-value which is greater than 0.5. So we narrowed down those parameters which are statistically significant, and then we started the stepwise regression using only those parameters. So when we ran the model with those limited set of parameters, now we don't have the DRG in this model. So without the DRG, the accuracy went up a little. There wasn't a big difference from 66% to 68%. There was a 1% increase. The next step in our regression modeling was to do a log transformation. Just as we saw in the in our plotting, we saw there were few variables which were skewed. We thought, okay, let's do a log transformation on those variables and see how the accuracy of the model goes up. So there wasn't a stark difference. It was almost in sync with that of the base model. So this is the final conclusion of the binary logistic regression model. So the average accuracy of our model hovered around 67 or 68% from predicting a patient with diabetes mellitus and DRG as a parameter. So one conclusion that we came from this logistic regression exercise is DRG neither affects or enhances the prediction. So DRG, it's not a stark parameter like what what we were thinking is it's going to alter it either positively or negatively. But one good thing is it's a neutral parameter. It's not going to bring the accuracy down, or it's not going to take the accuracy up. And as I said, the sensitivity of the model was like really high, and even the F1 score between the precision and recall, they were also pretty decent. So from all the aspect parameter, all the values that we saw, the confusion matrix output, uh, the model looked pretty decent. We were not able to say it to be like extremely good, but it is we were able to judge the model was operating at a pretty decent uh, accuracy. So once the binary logistic regression modeling was done, the next topic one we wanted to do was we wanted to see how the ensemble methods were working, ensemble models were working. Not only from in terms of accuracy, we also wanted to see the significant predictors in our model. So with that said, we started with decision tree. Decision tree gave an accuracy of 67%. One good thing that we learned from the ensemble models were the factors, variable importance factors. All these models, the decision tree, the random forest, the neural networks, or the XGBoost, all these models ranked DRG as fourth, or DRG was considered as top 5 parameter in prediction of hospital readmissions. So this was an eye opener for us. We started with an assumption that whether DRG even plays a role in readmission, but we were able to see that out of the top 5 parameters, model after model saying that DRG, yes, DRG is a significant parameter in terms of predicting whether a patient is going to get readmitted or not. So we have clearly listed out. This is an variable importance factor. This is the Gini mean decrease in Gini index, wherein DRG is a top 4 parameter. Similarly, we had even in the neural network, variable importance factor, DRG is a positive factor. And then even in XGBoost, we see DRG as the top 6th parameter. So this this is this clearly says yes, DRG is one of the key parameters in terms of hospital readmission rates. So as part of our final conclusion, this is what we figured out. One, we were able to see from an accuracy perspective, yes, we know like the maximum accuracy that we got was for neural network with smart analysis, wherein like instead of just picking ones and zeros in equal proportion, wherein we did a smart balancing uh, to make sure that the training data set is pretty good, and that particular model gave an accuracy of 92%. uh, so we have the link embedded because we did that particular thing in Python, not in R. So we had the link embedded with our complete code of that particular neural network with Smart. So coming back to the conclusion, what we discovered from this particular thesis is A, DRG affects hospital readmission rates, and B, DRG is the top 5 important parameter as well as hospital readmissions are concerned. With that being said, we feel as a next step, we wanted to find a pattern in which how hospitals are getting paid. That's the next step that we wanted to see. Okay, now having decided that DRG is a parameter, we wanted to see what is the pattern that they are getting paid. Is there anything in terms of uh, uh, payment that needs to be further provoked, or in terms of anything that in terms of billing that needs to be provoked. So these two areas we see it as future uh, as next steps or further scope for research. So with that said, we come to the final conclusion of our presentation. First and foremost, I would like to thank Jeff Neiman, our professor. The reason being, when we started this particular exercise, we wanted to uh, do it in a very surface level, this particular thesis, just to see whether a patient is getting readmitted or not. But he challenged us to go beyond what is currently there. With that thought process, we moved towards looking for whether DRG as a parameter plays a role in hospital readmission. We not only took up the challenge and we went down the path of getting the data, building a model, we are now able to conclude that yes, DRG is a parameter in hospital readmission and it is top 5 parameter in terms of how people are getting readmitted. So this so I would like to specially thank Jeff for pushing us to move towards the research that it's worth provoking, which is thought provoking. So thanks for the opportunity, and thanks CUNY uh, for uh, for uh, all the work and all the knowledge that we have gained. Thank you.